Hi folks, welcome back. Today I come to you with a paper from the very recently concluded USENIX annual technical conference, and it has a very interesting title because it is introducing a new abstraction, and that abstraction is called a transactuation. The idea behind this abstraction is how to carry over some form of the semantics of a software transaction into the physical world of IoT devices. This work was done by a team of researchers at Samsung Research. The problem that this paper tries to address is that of writing reliable applications for IoT devices. There are currently lots of solutions that let you write simple programs that can read sensors, read values from sensors, and then send back commands to do something like turn on an AC or a bulb or a smart lock and so on. You can get started with these pretty quickly. You can customize them and even write code to do custom things with them pretty easily. But the problem is that they have a ton of very subtle failure modes, and it's very tricky to correctly write code to handle all those failure modes. The root of the issue is guaranteeing consistency between states in your software, which this paper refers to as soft states, and states on the actual IoT devices themselves, which this paper refers to as hard states. So, for example, if you're writing code to turn on or off a smart bulb, you'll probably have some sort of Boolean variable in your code which says whether the bulb is on or off, and you might issue a command to turn the bulb on and then set this Boolean value to true. So whenever you write applications for IoT devices, you have a lot of this shadowing of state going on where state in your software tries to mirror the state of the actual physical device. And when these two, for whatever reason, fall out of sync, you end up in an error situation where, for example, you might think the bulb is on in your code, but it isn't actually on because something failed along the way. Here's a real world motivating example where a smart alarm was not correctly activated, and as a result of that, the customer actually got robbed while they were on vacation. If you look at the pseudocode for how the alarm is set off, you'll find that if it detects an intruder and the alarm is not already active, then it issues a command to set off the alarm. However, this command could fail due to radio interference, and that is actually a pretty common occurrence in smart devices. But if that happens, our code will still have set the alarm active Boolean variable to true, which will result in this not firing again when an intruder is detected. So we see how when soft states in our software and hard states in the actual device itself diverge, we can get into all sorts of error situations. Let's get some terminology quickly out of the way. The authors use the terms hard read and write to refer to reading and writing sensor or actuator values. A hard write typically means sending a command to an actuator. A soft read and write is reading and writing application states in your code that is issuing commands to the physical device. The authors enumerate a bunch of other failure states that an IoT system can get into. Another very common one is stale reads. Take, for example, an app that monitors CO2 levels and turns on or off exhaust fans when the levels rise. Now, if you read a sensor value to get the CO2 level, but it gives you stale data, then you will end up making an incorrect decision for when to turn on the exhaust fan. The one we saw earlier where the alarm did not go off correctly is part of a very common pattern in IoT code which is to have a soft state be an indicator of hard state in the device. Now you might ask why we do this. Why don't we just read the state of the hardware device every time we need it? And the primary motivation for that is to save battery on the device. If we need to read that state very often, it's much less energy intensive to do the read from the hardware just once, save that state in software, and refer to the state in software. The authors performed a survey of about 200 smart home applications and found a lot of these potential errors. And you can see how these errors are caused by various divergences between hot and soft state, or errors in sending an actuator command, or stale reads, or errors in reading sensor values, and so on. So hopefully by now the authors have convinced you that writing IoT device software is quite error prone. So how do we write reliable IoT software? To write reliable IoT applications, the authors are proposing a new abstraction which they call a transactuation. It's inspired by the idea of a database transaction, but is slightly weaker than that because obviously in the physical world you cannot always roll back all the actions that you have taken up to the point of committing a transaction. Just think of, for example, a water dispenser. You can't take back the water that it already dispensed. Transactuations provide two guarantees. First of all, they preserve consistency between hard states and soft states, which was a major cause of errors in IoT applications. And secondly, if you have transactuations that are executing concurrently, it ensures that they are properly isolated from each other. Let's look at a concrete example of how one would write a program using this new transactuation abstraction. A transactuation is broken up into three lambda functions: a perform lambda, a success lambda, and a failure lambda. If you've done promises in JavaScript, this is going to look quite familiar. Perform contains the real meat of your IoT logic. You can get sensor values and act on them and issue hard writes. Note that you cannot do hard reads inside the perform function. Instead of doing a hard read, you specify as parameters the sensors that you want to read and what policy you want to read them under. So for example, over here, you want to read the CO2 sensor. This number 5 is the time window within which you want to read it. This here means that you want a reading no older than 5 seconds. And these two are policies which state how many actuators you want to read and write. This says that you want to read all the CO2 sensors and you want to write to all the exhaust fan actuators. And instead of directly doing a hard read to get the values of the sensors, the framework provides you those values in a dictionary which you can look up. The success lambda is pretty straightforward. It gets executed if all these policies are met and the perform lambda completes successfully. And the failure lambda executes if the policies specified for the perform lambda, the actuating policy, the reading policy, etc., are not met. The runtime which supports this abstraction is called relax, and it contains a store which stores all soft and hard states in a dictionary. And this store is what abstracts out all the complexities of maintaining consistency between the soft state and the hard state and offering the transactuation abstraction. In terms of the implementation, all the states inside the store maintain two values, a speculative value and a final value. Speculative values are those that have not yet been issued to the physical device. only when the runtime receives an acknowledgement from the physical device that it has received a command or a value, it updates the final value and, so to speak, commits it and discards the speculative value. To get a sense for how easy this abstraction is to work with, the authors wrote several IoT applications three ways. The first one was just straight code without worrying about consistency or dealing with error conditions. The second way they wrote it was to handwrite custom code that deals with consistency and error conditions. And then finally, they wrote it using the new transactuation abstraction that they're proposing over here. And as you can see, using this abstraction gets you code that is just slightly larger than writing straight line code that doesn't even handle errors correctly, but much, much shorter than handwriting code to do it yourself. This paper was awarded the best paper at the conference, and I can sort of see why, because it introduces a much needed new high level abstraction in a domain that did not have a good programming methodology. So that was a paper that introduced a new abstraction called Transactuations that lets you write reliable IoT applications. I hope you enjoyed that, and I will see you next time. Thank you very much.